Nominal body stresses in screw threads can be useful to determine if the threads of the screw will strip. Stripped screws usually refer to three things: a screw with a head that is so bored out that your screwdriver or your screw bit on your drill can no longer get a good grip to tighten it or loosen it. Even though it doesn't refer to the screw itself, people call stripped screws any situation where the wood, drywall, or anything you're putting the screw through has stripped threads, but again, that's not really a problem with the screw itself. And finally, a screw where some, if not most of its threads have either plastically deformed or completely fractured because over-tightening it, making it almost impossible to extract. In the case of power screws, you don't want the threads to fail because the stresses were too large, since any permanent deformation will completely ruin the power transmission, the angular motion to linear motion transformation, or the consistency of the large forces that you are trying to obtain. In today's video, we will look at one approach to estimate the stresses at the threads of any kind of screw. We will find the reasonable stress types that are present at the critical stress elements within the screw, and we will calculate the von Mises stress for that critical location. The expression that we obtain will be a reasonable estimate to compare to what we will learn about the proof strength in a later video. If we draw a free body diagram of a screw, and let's take a left-hand thread screw to show that there's really not much of a difference in terms of stresses, we would see a distributed load on the surface of contact between the threads of the screw and the threads of the nut. By performing a vertical cut through the center of the screw, we can identify where the critical stress element is located. And the distributed load can be represented as a point load F between the root radius and the major radius, which we call the mean radius. Depending on the approach that you follow here, and specifically depending on the textbook or resource you're using, even depending on the different editions of the same textbook, you'll find that some of the terms might change, and even some of the stresses that yield small values might be missing. However, approaches similar to this procedure are still very useful when trying to obtain considerably more accurate estimates for critical stresses at the threads. The first stress that we can see here is the one due to a compressive axial load. The axial load that affects the whole screw root will cause a compressive normal stress that will mostly affect the root of the screw, and therefore the cross-section area will be that of a circle with a root diameter dr, and this stress is found on the planes normal to the y-axis, so we call it sigma y. Another normal stress is found on the stress element due to the bending caused by the force on what can be interpreted as a very wide cantilever, that is, the thread. This stress will be positive for the stress element in the figure, as the upper portion of the thread would be subjected to tension. I know this one is hard to understand, so let me paint you a picture, literally. The number of engaged threads are those threads that will be subjected to the load F. Let's say that 2.5 threads are engaged with the nut. If we unfold the engaged threads so that they're not in a spiral, but they look as a straight prism, the root of the screw would be the wall. The distributed load F would be substituted by a point load located at the center of the surface. The width of the cross-section area would be 2.5 times the circumference using the root diameter, since that is where the stress element is located, or in general, nt times pi dr, where nt is the number of engaged threads. The height of the cross-section area would be the pitch over 2. The moment at the critical stress location would be equal to F times the distance from F to that location, which is half of the pitch over 2, or P over 4. The variable y, the distance from the neutral axis to the top of the thread, would also be equal to P over 4. And finally, the second moment of area I would be that of a rectangle of height P over 2 and base pi dr times nt. Going back to our normal stress equation for bending, we would obtain a positive normal stress of 6F over pi dr nt p, which would be a normal stress in the x-axis. Because the torque that goes into the screw is what overcomes the friction between the nut and the screw, and this friction has a direction that is opposite to the sliding between them, you could picture that the thread around the root of the screw is trying to slide around the stationary root, therefore causing a pure shear stress on the surface where the threads and the root meet. This tangential shear force would be equal to the torque over the root radius, or root diameter over 2, and the area parallel to the tangential shear forces that cause the shearing stress would be the shaded area that has the same dimensions as the rectangle that we used for the bending. The resulting tangential shear stress would therefore be the shear force over the area, which results in 4t over pi dr squared ntp. And since it's a shear stress affecting the faces of the stress element that are normal to x and pointing in the z direction, we call these tau xz or zx since there needs to be a reaction on the adjacent face. The expression would in fact have a positive value for left-hand screws like the one in this example, and negative for regular right-hand screws, but you will see that the sign doesn't make a difference for what we are trying to figure out at the end. Finally, and due to the torque again, and not even looking at the threads, there will be a torsion stress for the solid rod that makes up the root of the screw. This shearing stress is just like the one of a rod, fixed at one end and subjected to a torque at the other end. As we move away from the fixed end, each disc that makes up the rod will be slightly rotated with respect to the adjacent disc, causing shearing. We know that this expression yields 16t over pi d cubed for any solid rod, and in this case, we're using the root diameter. This stress acts on a plane that is parallel to the discs that make up the rod, which is the top or bottom of the stress element, which means it's normal to the y-axis and in the direction of z, so we call it tau yz. The equations that we found here are assuming that all engaged threads are sharing the load equally. In practice, and because the screw is under compression and therefore its length and pitch is shortened, and the nut is under tension and therefore its length and pitch is stretched, the first engaged thread carries approximately 38% of the load, the second thread 25%, the third 18%, and the seventh thread is free of load. This is useful to us in that when we're designing a part that needs to be threaded to put a screw through it, as a rule of thumb, more than 6 engaged threads will not make the joint safer. It is also useful because we can estimate those stresses for the critical case, which is the first engaged thread that carries most of the load. The expressions that depended on the number of engaged threads, sigma x and tau zx, could be modified to have 38% of the force and 38% of the torque with nt equal to 1 thread. This would only be true for when the number of engaged threads are 6 or more. To put all of these stresses together, we use the von Mises stress. Now, we've done the process for writing the von Mises stress in terms of the principal stresses, sigma 1, sigma 2, and sigma 3. The difference here with what we've done so far is that this stress element is in 3 dimensions and 4 out of the 6 possible stresses do exist. Therefore, one of those 3 principal stresses will no longer be 0, like we've been used to. The only change here will be how the 3D Moore circle is drawn, but when we write sigma 1, sigma 2, and sigma 3 in terms of sigma x, y, z, tau xy, tau yz, and tau zx, we would find an expression equal to 1 over square root of 2 factor of sigma x minus sigma y squared plus sigma y minus sigma z squared plus sigma z minus sigma x squared plus 6 factor of tau xy squared plus tau yz squared plus tau zx squared, and square root of that. We see here that the sign of the shearing stresses doesn't make a difference in terms of calculating the von Mises stress, like I pointed out to before, since the shearing stress values are squared. Let's find out the von Mises stress for a square thread power screw that has a major diameter of 28 millimeters and a pitch of 4 millimeters with double threads. The torque that goes into the screw is 24 Newton meters. The first thing to know is that the force that comes out of the power screw can be calculated using what we learned during the last main video and the example videos that followed, links below. So I will not do that here today. But if we know what the collar diameter and friction coefficients are, we would be able to use that expression to calculate the output load F, which is the load that the power screw could lift. In this case, I will skip that and give you that F is equal to 5 kilonewtons. I know that to estimate the von Mises stress, I will need to use all 4 expressions that we derived today, and they, at the same time, depend on the root diameter, which I was not given. From a simple drawing of the screw, I would find that the root diameter is 24 millimeters. With that information, and the expressions we derived today, in terms of the force, torque, root diameter, and pitch, I would find that the values for sigma x, sigma y, tau yz, and tau zx are 37.8, minus 11.1, 8.84, and 5.04 megapascals respectively. Substituting these values in the von Mises expression above would give me a value of 47.8 megapascals. This is the stress that we will later compare to the properties of the material. As I mentioned at the beginning, for screws, we usually don't use a fracture strength or a yield strength value. In a couple of videos from now, we will look at what the proof strength means and how to look it up and use that property to calculate a factor of safety for this and other applications with screw elements. In the next video, we will look at fastener stiffness and member stiffness, two concepts that will allow us to calculate forces and torques for screws that are meant as non-permanent joints. Thanks for watching.